Hello, ladies and gentlemen, and welcome back. Root Beer here. We're looking at question C2 on our Canadian Open contest from 2018. Hopefully you've given this one a bit of a try. Let's have a look and see what we've got here. Alice has two boxes, A and B. Initially, box A contains N coins, and box B is empty. Okay. On each turn, she may either move a coin from box A to box B, or remove K coins from box A, where K is the current number of coins in box B. So she removes the coins. She doesn't move them. It's removed, so they're out. She doesn't move them to box B or anything. So if we got A has 5 coins and B has 2 coins, we could then get rid of, on the next move, A would have 3, B would still have 2, that sort of a thing. Now, what if am I allowed to do an operation like, B has 6 coins, can I still take 6 from, or does A have to have that many? They don't seem to be that clear in the instructions. Anyway, so K is the current number. She wins when box A is empty. Okay. So I got these two operations. You can move a coin or you can remove K coins. Alright, we got 3 parts here. A, if initially box A contains 6 coins, show that Alice can win in 4 turns. Okay. So A has 6 coins, B starts empty, they say. Well, I don't want to do the remove option, because then I'd remove 0 coins here and nothing would happen. So I guess we have to start with sort of the transfer a coin option. Transfer 1 coin over to B. So B can only go up by 1 each time. That's kind of interesting. A can go down by 1. Now, we can either transfer another coin and get 2 coins in B and get 4 coins in A, or we could just outright, I guess, remove the K coins, the 1 coin in B, and B would still have 1. I don't like that option because I feel like the bigger B is going to get, the more coins we can take from A, and so the faster we can get going. And so I feel like it's a waste when B has 1 coin to remove a 1 coin, or to remove that 1 coin when you could transfer and make B bigger for the next step. Just a thought. So we'll definitely do the transfer coin over option. And now we could remove 2. In fact, we could remove 2 to get 2, and we could remove 2 again. And that was step 1, step 2, step 3, and so on. After the 4th step, we're done. I don't think that's the only way to do it. You could do, I think the first 2 steps always have to play out the same way here. But we could move another one over, transfer another coin, and then on the next step, remove everything. So that would also take 1, 2, 3, 4 steps. So there's a couple ways to do it. We just need 1. They didn't say figure out how many ways she can win in 4 moves. Another observation, she can obviously automatically win in at least 6 moves. Just keep transferring coins out of A. But it looks like once B is 2, we can speed up the process and remove 2 coins at a time. But B is sort of stuck that way. But if we increase B, we increase how many things we can throw out. Interesting sort of set up these 2 operations and how they may interact with each other. We'll see what we need to know for B part. So B, if initially box A contains 31 coins, show that Alice cannot win. Cannot win in 10 turns. I assume they mean in 10 turns or less. Okay. So, even though we just have the 2 options, the remove option and the transfer coin to box B option, there's a lot of different combinations. We could do transfer, 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 remove, 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 or we could do transfer, 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 remove. There's a lot of different options we can play with. So obviously the number of transfers and the number of removes that we do, there's got to be at most 10 in total of those. But the order, I feel like the order might make a difference in some way. These operations aren't commutative, are they? The order should definitely matter. Yeah, the order has to matter because here, what did we do? We did a transfer, and then 2 removes. If we had done 2 removes at the start, and then done the 2 transfers, we would have been left with 4 coins. So the operation order does matter, and that means there's even more possibilities. So there's no way we could write them out. I mean, we could probably write out all the possible ways to do 4 steps, but 10 steps, that's a lot. So I think it's probably a better idea to start developing some theory and understanding what does a transfer do versus what does a remove do. So suppose I'm looking at a setup like this. Box A has A things in it. Well, no, they said N. Well, no, N's supposed to be the one they start with. So we'll say A, and box B has B things in it. Okay, so that's our setup. What happens if I do a transfer and then a remove? And I'm just trying to understand how these two play with each other. So if I do a transfer, I'll get B plus 1 and A minus 1. And then if I do a remove, still get a B plus 1 here, but I remove B plus 1. So I get A minus B minus 2 things in the end. What if instead I did a remove and then a transfer? So I'd get A minus B, B stays the same, and then I do a transfer, I'll get A minus B minus 1 and B plus 1. Now, removes never... So removes never change B at all. So the number of things in B will always just be the number of things you started with plus the number of transfers. But it does look like there's a difference in what happens to A. Here we removed 1 less coin, so it was more efficient to do a remove after a transfer. Is that always true? Could I prove that sort of a thing? Let's look at 3 operations, and then maybe there's a bigger picture we can see. So we'll do 3 operations. Let's do 1 transfer. So 1 transfer and then 2 removes. But not necessarily in that order, okay? So knowing that we're going to do 1 transfer, at the end we'll get B plus 1. Depends on where we do our removes. So suppose we do the transfer first and then the 2 removes. So we'll get B plus 1, A minus 1. And then we remove. So it'll be A minus B minus 2 we found. This is basically the same as what we just did. And then we remove again. We'll get A minus 2B minus 3. And then B plus 1. Instead, let's suppose we did a remove first and then a transfer. Well, we know how that plays out. A minus B, B. So there we did a remove, there we do a transfer, then we do another remove. A minus B minus 1, B plus 1. And then we'll do a remove. So that's A minus 2B minus 2, B plus 1. Same B's at the end, but I've got 1 less thing when I did my transfers before my removes. Let's do the transfer at the very end and see what happens. So we do the remove, do another remove, still says the same things in B, and then we do the transfer. B plus 1. And now it's still A minus 2B. And then, but instead of the minus 2 or the minus 3, we've got minus 1. Very, very interesting. What if I had two transfers and a remove? I'm not sure how much I can learn from here, but I'm trying to develop sort of a general theory. It looks like you have minus 2b. You always get a minus 2 times the number of removes. Then why would this be minus 1 versus minus 3 or minus 2? It has to do with the order of the removes and the transfers, I think. And there might be a general theory, and I might not be able to figure it out, but hopefully we can figure out enough to answer the question. So what if I did 2 transfers and 1 remove? Well, again, it's going to depend on the order in which we do things. Let's see if we can fit it all on one page. AB, AB. Just make a mental note. We're doing 2 transfers, 1 remove. AB. So here we'll do transfer, remove, remove. I think this will be the best option. And then how about we do remove, transfer, remove? I think that'll be the next best option. And then having our transfers all at the end seems to do less. I also want to make a prediction as to what I think is going to happen. Oh, sorry. I need 2 transfers and remove. We already did this stuff. Two transfers and 1 remove. Transfer, remove, transfer, remove, transfer, transfer. So I think this one's going to be the best. I think this is going to be the next best, and then this. And so I think we've got 1 remove. Looks like it's the number of removes. So I'm going to predict this is A minus B. And then, so I think this will be A minus B. Obviously, this will be B plus 2, no matter what, when we get down to the end of it. We've already made that observation. But in terms of what else we're going to have, I think this is going to be minus 2 because of the 2 transfers appearing before a remove. Does that make sense? No, this should be minus 2 because of the two transfers going after a remove. I think this might be minus 4 and this might be minus 3. Maybe you'll lose 1 every time you transpose a remove and a transfer. Could that be the possibility? Okay, so transfer does the same thing each time. Let's move these over. So the remove does this. Then transfer. Then transfer. And the transfers don't really... And yeah, we are going to get... exactly what I predicted over here. That makes sense. Okay, and then the removes, so that'd be A minus B. We already had the minus 1, now we're subtracting another one, so minus 2. And then we're just going to get rid of another coin. Interesting, 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 interesting. Another transfer, that'll be A minus 2, and then that'll be B plus 2, and then removing. It'll be minus B minus 2, minus another 2, minus 4. So it appears that the best thing to do is transfers, all your transfers before your removes. And anytime you move a remove before a transfer, you lose 1 overall. That seems to be it. Should we just state that as a rule, or should we try and prove it more conclusively? Not entirely sure. I think we can make a claim as to what happens if I do, K transfers and then 10 minus K for this particular question, but I'm trying to think broader, because it looks like these are the only 2 operations we're playing with. So it might be good to get sort of a general theory as sort of the best that you could possibly do. Might be a good idea. So, if we have k transfers and L, actually, we could say T yeah, the lowercase letters are small enough, or different enough. T transfers and R removes. I claim the best, or let's say the most we can remove from A is achieved by placing all T's before all R's. Okay? And then if I can prove it, I'll also do a follow-up and say what happens if you do an R before a T. And I think every time you've got an R before a T, you'll lose 1 overall. I'm not as confident in that, but it seemed to work out. Okay, so claim the most that we can remove from R. So if I have A there and I start with B here, in the end, what do I think is going to happen? Looks like the number of B's is the number of removes. And then 4. Why would it be 4? And why was it 1 here, but 3 here? That's the real question. Where are these numbers coming from? Something to do with the order. But I'm not exactly seeing it. Okay, well, after... not K, T transfers, you'll have A minus T and B plus T. I don't think there's any disputing that. I don't need to show where that comes from. And then after R removes, you'll have the A minus T, and you'll have R, B plus T's being subtracted, and you'll still get B plus T over here. We'll write that a little neater over here. So after TT's, A minus T, B plus T, and after R removes, A minus T minus RB minus RT. And that should explain where those numbers are coming from. So A minus RB, that's not in dispute from anyone. And then minus R plus 1 T's. B plus T. So a couple things I want to note. If we start with A having A things in it and B having B things in it, B can easily be 0. If we perform exactly T's, transfers, overall, B always has B plus T in the end. Okay? If we perform R's overall, A minus RB will occur, perhaps with more removed from A. Okay, so I know that it's going to be A minus RB. It's what is this number? I got that part done. I got that part done. What is this number? How does it depend on the order? So let's separate my transfers a bit more. I have A and I've got B, and I do a transfer, you lose one there. Actually, A will lose T. So we're actually guaranteed to get an A minus RB minus T. It's more about where did this RT come from. This RT is sort of what I'm claiming is the best we can do. So we'll get B plus 1. And now anytime we do a remove after this, this plus 1 is sort of removed. So any R's after this transfer, this plus 1, I think I'm going to color code this. I think this might be sort of easier to understand. So I'll do A, B. I'll do some more A, B's, and maybe another A, B. So if I do one transfer, I'm down 1, I gain 1 here. That's for this transfer. And that also, I mean, that carries through. But then if I do another transfer later, I'll have lost another 1 here and gained another 1 here from then on till the end of time. And then if I do another transfer down here, fine. Now, anytime I place a remove, I'll be removing whatever's currently here. So if I put a remove here, I remove the B that I knew I already had, but I'm also removing this plus 1 again. Okay? So for every transfer, count the number of R's that appear after it. So every time, so this R here is going to remove this plus 1 again. But it's also going to come along and remove this plus 1 that came from this transfer. So for each T, count the number of R's that occur after. Each T moves 1 coin to B, and each R after this T compounds this by removing 1 more coin from A. So start with A and B and B, and I do KTs, and the sum of the number of R's appearing after each T is equal to, let's say, oops, I keep saying KTs. I want little t. Because now I can use K in a more appropriate place. So let's call this K. And we've got RRs. I think at the end we should have A minus RB minus T minus K. And I think it should be B plus T over here. So I think that's the case. I might have to tweak it slightly, but let's go back and see what we have seen so far. Okay, it would track here because after each T, there are RRs, because all the R's take place after all the T's. So we would have a sum of TRs, or RTs, and that's exactly what we're seeing here. Whereas if I go back to, say, this one, there are no R's after these T's. And you'll notice I have minus 1B, minus 2, which is the number of transfers, and nothing else. Here it's the minus the 1b minus the 2 coming from the transfers, and then after this t there is an r, but after this t there are no r's, so we get minus 1 r after a t. For each of these t's, there's one r that appears after it, and that's why we get an additional minus 2 from the already a minus b minus 2 that we would have. So this tracks, and we have demonstrated it. You know, color code it with a little extra sentences, and we've got our result. Okay, now I understand exactly how these operations go, and I can say for certainty that yes, having all your r's after your t's works. Okay, so that was a heck of a diversion, but now I think I sort of fully understand exactly what these two move and remove coin operations do, which is great. Hopefully, unless they throw a curveball at me in part C, I'll be able to do B and C quite quickly from here. Okay? So now for B, we want to show that with A starting with 31, and B starting with 0, we can't do it in 10 moves. So we'd have T transfers, and then we'd have 10 minus T removes. All right? So automatically at the end, just from knowing that, I'm guaranteed to get A minus 10 minus T B's, which in this case is 0, minus T from each transfer, minus some K. Okay? So this is 31 minus 0 minus T minus some K. At most, K can be, we've seen, is RT, which in this case is 10 minus T times T. That's the best you can do, and that's if you place all the R's after the T's. So with 31 minus T minus 10 minus T, T, and I want this to be less than 0. Less than or equal to 0, because that would mean that everything has been removed from A. So the complaint I made at the start, like, can you take 6 things out of a box of only 5 coins? I'm saying, yeah, you can go into deficits. It doesn't seem like it's going to cause a problem to the reasoning for the problem. So what I want to do is show that there is no t from 0 to 10 that makes this formula work. And it's a parabola, so we should be able to do this. So 31 minus t minus 10t plus t squared less than or equal to 0. I'm willing to bet that this parabola, it's an upward-facing parabola. I don't think I can factor it, but let's put it in. Vertex form is going to be a heck of a problem, but we can do it, I guess. So 11 over 2 squared. That's 121 over 4 minus 121 over 4 plus 31. So that'll be t squared minus, t minus 11 over 2 squared minus 121 over 4 plus 31. 31 we can rewrite as 124 over 4. So t minus 11 over 2 squared, which is always non-negative, plus 3 over 4 has to be less than or equal to 0. Impossible. See how easy that was? Now that I understand exactly what how this process works, what you can end up with, the most that we can have, and I understand why it is, you have to put your removes after your transfers because I understand how each transfer and remove affect each other. Very, very quick A part, now that I've got the theory built up. So I know that's impossible, so therefore can't be done in 10 moves. I don't know why I'm doing it in all caps there. Okay, interesting. Now, what do we got at C part? Hopefully this doesn't change the game. It's a small sentence, so I'm willing to believe that they're not introducing another operation or something like that. What is the minimum number of turns for Alice needed for Alice to win if box A initially contains 2018 coins? Okay. So, minimum number of turns needed. Interesting. Well, let's talk about, let's say, M, the number of turns she needs, and see what conclusions we can draw. So, let us inquire to what M. Well, sorry, let's say whether she can do it in M turns. Well, then I would need. So we're starting with A is 2018. Again, we're starting with B is 0. And so after M turns, let's say T transposes, and then M minus T, not transposes, transfers, and M minus T remove operations, we get A minus M minus T B's minus T minus K. And I know what K at most can be. Okay, but B is 0, so we can ignore this. So it's 2018 minus T minus K. At most, K is M minus T times T. So I want 2018 minus T minus M minus TT to be less than or equal to 0. This must hold true. And the number of things left in A after all these steps must be less than or equal to 0. If we cross the 0 line at some point, so be it. Okay, so 2018. In fact, because we lose 1 coin every time we swap the operations, even if we were to jump down to make it minus 2, we can just reorder the operations to make it a clean jump to 0. Yeah. Anyway, so minus T minus MT plus T squared less than or equal to 0. Almost the exact same stuff. So M plus 1 T plus 2018. Let's complete a square, although this is going to be a little more awkward. So plus M plus 1 squared over 4 minus M plus 1 squared over 4. Oops, need the 2018, which I'm going to say is 8,072 over 4, just to make our life a little easier. So I'll have T minus M plus 1 over 2, all squared, plus 8,072 minus M plus 1 squared, all over 4. This needs to be negative. Okay, at best, the T equal to M plus 1 over 2 makes T minus M plus 1 over 2 squared equal to 0. So we definitely need 8,072 minus M plus 1 squared over 4 to be less than or equal to 0. Okay, if I can get that to be less than or equal to 0, I can choose T to be M plus 1 over 2. I'm ignoring just for a moment the fact that maybe that T isn't an integer. We'll deal with that in a moment. Right now, I just want to sort of figure out some M possibilities. So multiply by 4 on both sides. We need M plus 1 squared. Okay. This is close, I guess, to 8,100. So this is an integer square. So m plus 1 squared must be at least 8100. So square rooting 90 must be at least m plus 1. And so 89 has to be your smallest m. The question is, can we actually do it? Well, I'm happy with the fact that m plus 1 is going to be even, so I can divide by 2. So I know m has to, so we can't use less than 89 moves, definitely. But will 89 moves suffice? Okay, that's the challenge. So, okay, what do we do here? So, I guess to show it suffices, we do actually need to explain, do this number of steps, then this number of steps. All right, I think. So, I guess we have to. I'm going to try and solve the equation so that it's equal to 0, not necessarily less than 0, because it's their fault that they weren't clear as to whether or not, if I've got 6 in B and 5 in A, I can do the remove operation. They didn't say you can't do it, but don't assume, because they, the people who made the contest might have thought, oh, it's obvious you can't remove if you don't have enough coins. But I'd say that's their problem. That's their fault. They should have said when I can't do an operation. But okay, let's try and solve this. So 89 plus 1 over 2, so 45. So t minus 45 squared plus, is this going to be an integer? 8072 minus 90 squared. I want to solve this to be equal to 0. It might be that it doesn't work out as actual. Yeah, because it'll be minus 100, so it'll be minus 28 over 4. So t minus 45 squared. That's not a square. But of course, this was sort of our upper bound. Could I make this equal to a square? What's the next possible square? It's a 37. Sorry, not 37. So if I did 36, then this would be 9, right? And then I could let t be something like, well, it could be 42 or 48, doesn't really matter which. Well, okay, that's not true. It might very much matter which. So if I want it to be 36, I don't want 72 here. I want 64. And so 8064 is less than 8072. So how can I make that happen? So let's say something like t equals 42. And so then so that's how many transfers of coins we'll have. So r needs to be 47 to make 89. And so at best, what can I have? That k value at best can be 42 times 47. This is where I wish we had calculators. We don't. 9, 0, 8, 2, 18. Wait a minute. 8072 came from the 2018. So none of this is good. So how do I fix this? So instead, normally we'd have (2018) minus t minus k needs to be less than or equal to 0, right? That's what we learned. And so I should be able to find an m, or so m with 89 works. This is not nice. This is not nice. I'm gonna stick with my 42 and see if I can find a k that'll work with that. K can be any value. We've seen it. Any value between 0 and m minus t times t, which in this case is now 89 minus t times t. Right? If you have all your transfers after the removes, then it'll be 0. If you have all your removes after your transfers, it'll be this amount. And as I've said, swapping a remove and a transfer seems to lose one each time. So in this case, it might not have to be 42, but let's see. 2018, so 2018 minus 42, we'll get, it'll end in a 6. 2016 minus 40, 197, 6, and then 89 minus 42 times 42. That'll be 47 times 42. Didn't I just work that out? Yeah, it's 1880. That's not big enough. So, should we try something closer? Actually, what if I try 45? What if I just try t as 45? Because that seems to sort of be the middle ground. So that'll be 1970. Oh, wait, no. Why is this 1880? Oh, no, that was the bottom number. So it should be 4, 7, carry the 1. So 1974, which is still less than 1976 that we had before. But now that I've got 1975, I will have 89 minus 45 is 44 times 45. That's 22 times 90, and so that'll be 1980. So that should work. Now, what do I want to do? I want to remove 7 of them. So I'm claiming do 44 transfers, then 7 R's, then 1 transfer, and then the remaining, it's got to be 44 R's, so 44 minus 7 would be 37 removes. And that should do the trick. Because now these 44 transfers give me 44 removes for my K value. And then this 1 transfer only has 37 removes to its name. 44 times 44 is 1936. No, I don't think that's right. 44 times 44, 6, 1, 7, 1, 0, 6, 1, 7, 1, 6, 3, 1, 9. Yeah, it is 1936. Plus 37 is 1970, which is exactly what I just asked for. So it works out. There we go, and I've actually shown how it can be done, and I'm only using 89 steps. And we also showed earlier with our quadratic, 89 is the best you can do. So there we go, all done. It took a while. I would say actually the other than this little trying to sort things out definitely at the end of C, which they might not even have been asking for in the marking scheme. I would say most of the time here has been devoted to figuring out exactly how the remove steps and the transfer steps interact, and it's, I would say, a very nice little theory. How much did you actually need to show? Could I have just claimed things like swapping a remove and a transfer always decreases by 1? Could I have just claimed what the best you can do is and what that calculation is? I don't know. Having read past open solutions, they're a little loose on the rigor with some of the things that they need in C part. So you do your best to judge. It's always a good idea to read solutions, not just watch me, but read the solutions that they post online, because those are very similar to the marking schemes. And try to show as much work as they do, because that's what they're looking for. Sometimes I'm a little too rigorous, sometimes I'm a little rigorous-less, and I should be adding more sentences and things like that. But there we go, that's C2. Up next will be C3. We are halfway done Part C of our paper. I will see you for more of the 2018 paper next time. Until then, take care.